Let's recall the standard topology on Rn. We have a distance between 2 points in n-dimensional space, given as usual by the square root of the sum of the squares of the differences of coordinates. And from using that distance, we can form open ball of radius epsilon centered at x, which is just the set of all points p whose distance from x is less than epsilon. And the collection of all such open balls is a basis for the standard topology on Rn, n-dimensional Euclidean space. Okay, so exercise 2.20, prove theorem 2.11. Let A be a subset of Rn in the standard topology. If x is a limit point of A, then there's a sequence of points in A that converge to x. Okay, so this makes sense linguistically, if nothing else, right? If x is a limit point of A, then it should be the limit of a sequence of points in A. Okay, but there's a little bit of work to show that the definitions all work out. All right, so it's really a two-step proof. First of all, we have to show that we can construct a sequence, sort of say what it's going to be, and then we have to show that it actually does converge to x. Okay, so to construct the sequence, we can say since x is a limit point of A, the neighborhood, the open ball centered at x of radius 1 over n, right, that's a basis element, and so in particular it's open, and it does contain x, so it's a neighborhood of x, contains some element, let's call it x sub n, in A, which is not equal to x, although I'm not going to need that last fact, which is why I put it in parentheses. Okay, so this is just from the definition of limit point. You take any neighborhood u, which I'm taking this particular one, of x, and it has to contain some element of A other than x. And the one that's contained in this ball of radius 1 over n, I'll call that x sub n. All right, and I can do this for every positive integer n, and so in that way I get a sequence. So in this way we define a sequence of terms x sub n. Okay, good. And well, it's not just a sequence, right? This is a sequence contained in A. Okay, so I should add that here. Every x sub n is in A. Okay, so now we need to show that this sequence of points in A does converge to x. Okay. Now we must show that x sub n converges to the point x. And, well, you recall our definition for convergence in a topological space. Basically, given any sort of neighborhood U challenge, you have to come up with some capital N response. Okay, so we are going to be given a neighborhood U of x. What can we say? Well, there exists some epsilon such that the ball centered at x with radius epsilon is contained in U. Okay? And that is by theorem 1.9. It was the, well, it's sort of a local criterion for openness, right? It says that that this U is open if for any point x inside of it you can find some basis element of the topology which is contained in that open set U. Alright, good. Now let's choose our capital N in the positive integers so that 1 over it will be less than or equal to this epsilon that we've found. Okay, and then from that if we have n greater than or equal to n, which we're allowed to assume, that implies, taking reciprocals, that 1 over n is less than or equal to 1 over capital N, okay, which we just wrote down. Let me write it again, is less than or equal to epsilon. And so, well, so what do we know about x sub n? Right, I'm trying to show that whenever little n is greater than or equal to capital N, that x sub n has to be in U. Okay. Well, I know that x sub n from up here is contained in this neighborhood, in this open ball about x of radius 1 over little n, right? But because 1 over little n is less than or equal to, well, less than or equal to epsilon, that ball is contained in the ball centered at x of radius epsilon. And that ball is a subset of U, right? That's that basis element that we found contained in U. So put it's a subset in U, and we're done, right? We've shown that given any neighborhood U of x, we were able to find some capital N such that all terms of the sequence starting at that term are going to be contained in that given neighborhood U. All right.